The next speaker is Joan Bagaria from Barcelona, from both ICREA and the University of Barcelona. And he will talk about Superstrong and huge reflection. Yoroshiku onegai shimasu.
Thank you, York. Well, it's a really great pleasure to be here, sharing with all of you this celebration for Sakai Fuchino's retirement. Actually, as York pointed out, he retired some time ago, and I must say I haven't noticed any difference in his math production. So, on the contrary, it seems that he's working more than ever. So, keep it up. That's very good news. And yeah, I know of several examples of great mathematicians who have been much more productive when they were retired than during their normal their normal activities. So I'm sure this will be also the case of Sakai. And well, enjoy the new period of life that opens up in front of you. And of course, you should spend also some time playing piano. Of course, I'm sure you will. But anyway, do the things that you really enjoy. Now it's the time to really enjoy the years ahead. Okay, so I want to talk about reflection. This is a topic that I like very much, and I know Sakai also likes it very much, and he's been working on different kinds of reflection for many years. I want to talk about is something I call structural reflection. That's a topic that I've been working on and off for the last 10 years at least. And there are several papers with different people containing some results on structural reflection, how this principle of structural reflection under different forms can be used to characterize well-known large cardinal notions. And there have been also some applications to algebraic topology, homotopy theory, and so on. But so today I will talk about these some recent results. And the point of my day is to look at the region which is quite high in the large cardinal hierarchy. So these are very strong structural reflection principles. And the structural reflection we have been studying up to now somehow was in the region below Vopenka principle. And so today, at the end of my talk, the second part, I will also give you a first a quick overview of some recent results that we have obtained with Philip Lücke, who is also here attending the workshop. I will only mention some of these because this is still going on work. But anyway, this is, I think it's interesting because it gives some results on structural reflection that characterize large cardinals that go beyond Vopenka's principle. So let me just start. Let me remind you of the general structural reflection principle. It's a very simple thing. It just says that for every definable in the first order language of set theory, you may have parameters, a class of relational structures. By this we mean structures with relational in a relational language, which we may assume it's countable. So for every such class of relational structures of the same type, there exists an ordinal that reflects the class, which means that for every so there is some alpha here that reflects the class. So if you pick any structure in the class, there is one below alpha, and there is an elementary embedding from V into A. Okay, so this is the kind of reflection we want to look at. Right. So go back to this. Of course, if you want to formulate this kind of principle in a precise way or in a logically sound manner, then you need to formulate it as a schema. So for every definability class, so say sigma n or pi n, and you may take a set of parameters or a class or even a class of parameters. So we look at the sigma n structural reflection with parameters in P is just the same principle, just says that for every sigma n definable class of structures of the same type, using maybe parameters in P, there's an ordinal that reflects the class. And the same or similarly for the pi n definable classes. Now, a few years back, in a couple of articles that you have here at the bottom, we showed the following. We showed that this principle, when it's restricted to sigma 1 definable classes, this is just provable in ZFC. Okay. For pi 1 or sigma 2 definable classes, this is just the existence of a supercompact. So by this, I mean that the principle holds for some cardinal kappa, let's say, so some cardinal kappa reflects the all the pi 1 definable or sigma 2 definable classes of relational structures, even only if it's the least one, then this is even only if it's the first supercompact. Okay, so there exists such a cardinal even only if there exists a supercompact cardinal. Every supercompact cardinal does that, and the least one that does this kind of reflection must be supercompact. If we go one level higher in terms of definability, so we look at pi 2 or sigma 3, then what we get is just an extendable. So every extendable cardinal reflects all pi 2 definable or sigma 3. By the way, we always get this pattern, right? So because that's a general it's a general fact that reflection of this kind for pi n or sigma n plus 1 is equivalent. So in the case of pi 2 or sigma 3, we get extendable, meaning that every extendable cardinal does this kind of reflection for classes of this complexity, and the least cardinal that for which this structural reflection holds must be extendable. And then we keep going up the hierarchy. So for more complicated definable classes, we need the notion of Cn extendable, that it's exactly like the definition of extendable, in which so kappa is Cn extendable if for every, say, lambda bigger than kappa, there is an elementary embedding from b lambda into some b mu, right? Such that J of kappa is bigger than lambda, and J of kappa, that's the key point, belongs to Cn. Cn means Cn is the class of all kappa such that V kappa is a sigma n elementary substructure of V. Okay, so it's just this notion of Cn extendability is the notion that you need to characterize this structural reflection for the higher complexity classes. Right. So I need to erase this, otherwise it keeps appearing in all the slides. Right. Let me go. Next one. Why doesn't it go there? Now. Okay, so a different kind of structural reflection is what we call product structural reflection. So it's essentially the same thing, but now what we have is, again, we have some class of structures of the same type and definable. We only look at definable classes. So we are always in the context of ZFC. So this says that for every structure in your class, there is a set of structures also of the same type, maybe not in the same class, doesn't matter, but which contains this structure A, and there is an elementary embedding from the product of all the structures in your class at below alpha, below level alpha, into this product. Yes. So now it's not reflection from a structure in the class to another structure that lives below alpha, but it's a reflection, or if you want, it's not an elementary embedding from a small structure in your class into the structure A, but now the elementary embedding is between the product of all the structures that live below alpha into the product, into some product, which has to be necessarily of structures of the same type, but in which one term in this product is the structure A. Okay, that's the product structural reflection. Again, this kind of reflection, sorry, this kind of principle, why doesn't it go? Sorry, something this, okay, let's see now. Oh, there. So this, again, to formulate this properly, you need to do it as a schema, right? So that's the right formulation. Yeah, I should also remark that here we are talking about arbitrary classes of structures, but in fact, we can, in all cases that I will talk about today, and in fact, in all relevant cases, I know, one can restrict to structures of this form, in which the structures in which the domain is some V alpha, okay? So these are what I call natural structures. All right. Oh, sorry, no. Yes, here. Okay, so what happens with product structural reflection? Again, we have a nice characterization. So for sigma 1 classes, this is just provable in ZFC. For pi 1 or sigma 2 definable classes, this is just a strong cardinal. So again, every strong cardinal reflects all classes of this complexity. And the first cardinal that reflects that product, when I say reflects now, I mean product reflects classes of this complexity, has to be a strong cardinal. And for the remaining levels, there's the notion of pi n strong. And if you have it for all definable classes, then what you get is the notion of or this would-in. So let me just tell you what this means quickly. The notion of strong cardinal is well known. So it just says that kappa is strongly for every ordinal lambda. There is an elementary embedding from V into M. Intransitive with critical point kappa, and V lambda is contained in M. Now, the notion of sigma n strong is just the same as this, but we, in addition, what we require is that for any sigma n definable class A, A intersected with V lambda is contained in J of A. Okay, so the class A somehow is preserved or respected up to lambda. Yes. So that's the notion of sigma n strong. So strong is sigma 2 strong, but then if you will look at sigma 3, sigma 4, this forms a hierarchy, strictly increasing hierarchy. Right. And again, we also have this this phenomenon that provided that lambda is sufficiently correct. So if lambda is sigma n plus 1 correct, then lambda pi n strong is the same as lambda sigma n plus 1 strong. So pi n strong is the same as sigma n plus 1 strong. And what about or this would-in? What does it mean? Well, if you know the definition or the characterization of a would-in cardinal in terms of A is strong in terms of where A is some class, then you will see that this is essentially the same. But of course, now we are looking only at definable classes. So, or this would-in, it means that for every definable class, there is some some alpha, which is a strong, meaning that it's strong in the usual sense, and the class intersected with V gamma is just J of A intersected with V gamma, right? So again, this is just like the characterization of Wooleyness for a cardinal, but now we are talking not about the cardinal, but about the class of ordinals. And therefore, since we are in the ZFC context, we can only consider definable classes. Of course, if delta is Wooleyan, then if you cut at the Wooleyan cardinal, then this you get a universe in which ORD is Wooleyan. So here's the table again. So we have this nice equivalence, okay, between those notions of product structural reflection for corresponding definability classes of a given complexity and the corresponding large cardinal. Okay, so if you have a product structural reflection for all definable classes, this means that exactly this is equivalent to the ordinals being Wooleyan. Okay, now when looking at the proof of one of these facts, namely the fact that if kappa is pi n strong, then you get a structural reflection, product structural reflection for pi n and sigma n plus 1 classes, then you see that the proof gives you more. In fact, the proof gives you that there exists a set S of structures of the given type that contains, so for every beta, there is a set of structures of the given type that contains all the structures in your class up to beta. And then there is an elementary embedding from the product of all structures in your class below kappa. Kappa is the cardinal that reflects into the product of S. So S contains all the structures up to beta. So in other words, that you can reflect, so you can go as high as you want, look at all the structures in your class there, then take the product. Maybe you have to enlarge this product a little bit, but anyway, there will be an elementary embedding from the product of all the structures in your class below kappa into the product of this set. Okay, moreover, this embedding has two further properties. One is that this embedding is faithful, which means that if you pick anything, any F in this product, then the image under this elementary embedding, when restricted to the product up to kappa, will be just F. Yes. And this in general need not be this way, but it so happens that this is true because actually the embedding, the elementary embedding H is not just any elementary embedding, is an elementary embedding that comes from the elementary embedding from V into M given by the pi n strong cardinal. So this is a bonus that you get. A second property is what I call subset chain preserving, which means that if you pick any function in the product up to kappa of structures in your class up to kappa, and this function has this property, namely that whenever a structure A in your class is contained in structure A prime in your class, then the image under F of A is contained in F of A prime, then this property is also translated or transmitted to its image. So H of F also has this property, okay? So this you get for free, assuming that kappa is a pi n strong cardinal. You get this product structural reflection, but with these two additional properties. And it turns out that these two additional properties are exactly are exactly what gives you large cardinal strength. So we will see this in a minute. So we can reformulate the principle of product structural reflection by incorporating these two properties. So now we require that that for every beta there is a set of structures of the same type that contains all structures in your class up to beta, and you have an elementary embedding from the product of all the structures in your class up to kappa into the product of the set, which has these two additional properties, so being faithful and subset chain preserving. Okay. And now we have the theorem. We have that there is one single class of structures that is pi1 definable without parameters, so that if you have a cardinal that product reflects this class in the sense that I just stated, then kappa must be a strong cardinal. Okay. What is this class? This class is just, it's very simple. It's just a class of all structures of this form. The domain is V sub lambda alpha, where alpha is the alpha element of C1. C1, remember, is the class of ordinals that are sigma 1 correct in the universe. So alpha is the alpha element of C1, and lambda alpha is the least cardinal in C1 greater than alpha. So this is, it's easy to see that this is pi1 definable. And if we have a product reflection for this class, yes, in the sense that I've just explained, then kappa must be a strong cardinal. So the theorem is the following, that the cardinal is, can you see this? Can you see the bottom? Because this is, I can move this somewhere else. Yes. So a cardinal kappa is pi n strong, even only if it witnesses the product structural reflection. So this characterizes pi n strong cardinals. Okay. Exactly. So it's not just that the pi n product structural reflection holds even only if there is a pi n sum. No, this gives an exact characterization, and the reason is because we have these two additional conditions of being faithful and being subset chain preserving. This gives us a full characterization or exact characterization of strong or pi n strong cardinals. Okay. So for strong, this is just n is equals 1. So cardinal is strong, even only if it witnesses pi1 product structural reflection. Right. So now, of course, one can look at a slightly different form of product structural reflection, which is, I think, even more natural, namely the following. So you say that that for every, so again, we have a class of structure. This is the general form, okay? So this is not the precise formulation because it needs to be formulated as a schema. But in general, this what they call strong product structural reflection says that for every structure in your class, there is an ordinal above the rank of the structure and an elementary embedding from the product of the structures below your reflecting ordinal alpha and the product of all the structures up to beta. Yes. Okay. So since we are in a, I mean, all this discussion makes only sense in the case C is really a proper class. So what this is saying is that this strong product structural reflection says, well, there is a level alpha such that if you look at the product of all structures in your class up to that level, this product can be elementary embedded into arbitrarily high products of all the classes up to any given rank. Yes. So this is I think the natural form of product structural reflection. Okay. Now, let's see how this goes. Right, again, so the proper formulation is the schema. So, okay, so what the question is, does this notion of product structural reflection, which we call strong product structural reflection, correspond to any of the known large cardinals? Well, it does, and the large cardinals that it corresponds to are what are called globally super strong and globally super strong, and the corresponding CN versions of these. So these are cardinals that were studied in a paper by Jinglun Tsai and Kostas Tsabrounis, published in 2019. So let me tell you what these notions are. Well, the notion of super strong is well known. So kappa is super strong above lambda if, well, no, this is, I mean, this is superfluous. Sorry. If there is, yeah. Well, okay, so kappa is super strong above lambda, where lambda is some ordinal, at least it's bigger or equal than kappa. If there is an elementary embedding from V into M transitive having critical point kappa, the image of kappa is above lambda, and that's the super strength condition. Vj of kappa is contained in M. Okay. Okay. Now. So why doesn't it? This is a bit annoying. Okay, yeah, there. So then we say that kappa is globally super strong if it is super strong above lambda for every lambda, so for arbitrarily large lambda. Okay, we have the similar notion if we put the CN requirement, namely it's the same thing, but now we require that the image of the critical point belongs to CN. And we say that kappa is CN globally super strong if it is CN super strong above lambda for every lambda for a proper class of lambdas. Okay, so that's the notion. Well, how strong are these cardinals? Well, if kappa is CN globally super strong, then there are many CN super strong cardinals below kappa. So globally super strong is much stronger. But they are all rather, well, they're rather mild in the sense that if kappa is one extendable, so if it's kappa plus one extendable, then V kappa, if you got the universe at kappa, satisfies there is a proper class of CN globally super strong cardinals. So consistency wise, these cardinals, and this is simultaneously for all n, okay? So this is, sorry. So this is CN globally super strong for every n simultaneously. So there's a proper class of cardinals, say lambdas. I said lambda is CN globally super strong for every n. Let me erase this. Okay. Well, anyway. I don't know how to do this. Okay, now. And also if kappa is CN extendable, then outright, then there are many CN globally super strong cardinals. So we are below Bopenka principle. Bopenka's principle is just equivalent to the existence of a CN extendable for every n. Okay. Well, if kappa is CN globally super strong, then it witnesses this strong product reflection principle for pi n definable classes. Again, the proof of this also shows that you get a bonus. So you get this faithfulness and subset chain preserving properties. So we can just reformulate this principle and we get an equivalent principle that has these additional requirements. Okay, so we say that kappa strongly product reflects all classes if for every, or reflects a class C if for every structure in the class there is some ordinal bigger than the rank of A and some faithful and subset chain preserving elementary embedding from the product of all structures up to kappa to the product of all structures up to beta. Okay. Okay, now we can prove this similar thing as in the case of strong cardinals. So there is one single pi-n definable class of natural structures such that if a cardinal kappa strongly product reflects this class, then it has to be a CN globally super strong. I will, let's see how much time I have. Good. So I will sketch a little bit the proof. I chose to sketch this one and not the previous one for a strong, because this is, for the one thing, I think this notion of product reflection is more natural, and also it's nicer. I mean, the proof is somehow nicer. So, but I want to sketch it because I want you to see what is the relevance of these two additional properties of faithfulness and subset chain preserving to get the large cardinal. Okay. Right. So let's see that. Okay. So what is the class? The class is the same one as before. So we take the class of structures of this form. Okay, so these are structures whose universe is a rank initial segment of the universe is a V lambda alpha, where alpha is the alpha element of Cn and lambda alpha is the least cardinal in Cn greater than alpha. Now, suppose we have a kappa that reflects this class. So it witnesses in this strong sense, okay? And then we look at I, the set of alpha, such that A alpha is in V kappa. Well, one can check that kappa must necessarily be in Cn plus 1. This needs to be checked, but that's true. And so it follows that the supremum of I must be kappa. In other words, that there are structures in the class of arbitrary high rank below kappa. So now we pick some ordinal bigger or equal than kappa, and we need to show that kappa is lambda Cn super strong. And that's what we want to show. Yes. Okay. So so let's pick some A beta in C, where beta is bigger than lambda. Okay. And pick some cardinal kappa prime such that A beta belongs to B kappa prime. And there is a faithful and subset chain preserving elementary embedding from the product of all the structures up to kappa into the product of all the structures up to kappa prime. That's our assumption. There is such a thing. Okay, so now if we pick any structure in our class that lives in V kappa prime, we can take the projection. So we project the product of all the structures up to kappa prime into this particular structure, and we call this projection map H sub beta. Now, the important thing here is that J was an elementary embedding, but when we project, this is no longer an elementary embedding. Okay, this is just a homomorphism, and that's one of the difficulties here, because now in order to produce the extender witnessing that that kappa is lambda Cn super strong, we cannot do it in the usual way. I mean, there are several difficulties at this point, because the embedding from which we get the extender is no longer an elementary embedding, but just a homomorphism. All right. So now we look at, we define the following map from V kappa plus 1 into V beta plus 1 in this way. So what is the image of some X? X is a subset of V kappa. So we look at the trace of this set on the V alphas, okay? And we look at the image of this trace under J. Once we have that, then we project it into A beta. And that's how we define this map. Okay. So it's the projection of the image under J of the trace of X on the V alphas for alpha in I. Right. Now we can define, now we obtain an extender from this. So for every, in the usual way. So for every finite subset of beta, we get the corresponding ultrafilter defined in this way. So something is in the ultrafilter if and only if it's a subset of all subsets of kappa of size, the size of A, and A belongs to the image of X under K beta. Okay. Now it's a matter of checking that this is an omega 1 complete proper ultrafilter, and therefore it's well-founded. The ultra power is well-founded. Now here is the first use of faithfulness. So because J is faithful, if we have a beta in I, then this is just the principal ultrafilter generated by A, okay, by a singleton A. Okay, so now we get this extender, and one can show that it is indeed an extender, that it has the usual properties of normality and coherence. This takes a bit of work, but not too much. So we can get the extender direct limit. Okay, so we have all these models, the corresponding elementary value. This, as I said, this is just a sketch. I assume most of you are somewhat familiar with this kind of construction, so I will not give more details than that. And then we take the corresponding limit elementary embedding that corresponds to this extender for beta, for a given beta. Okay. Right. So again, one can show that this is well-founded. So we can take the transitive collapse and get the corresponding embedding from V into this transitive collapse. Two things need to be checked. That again, it takes a bit of work. First of all, that V beta is contained in N beta, so that this embedding is beta strong. And also that the image of kappa, we don't know yet if kappa is the critical point, but at least we know that the image of kappa has to go at least up to beta. Okay. And of course, if we picked a beta that was greater than kappa to start with, then already gives us that the critical point of the embedding is at most kappa. It could be less, but is at most kappa. Now, here is the other key point. So if we do this so this is what happens for any beta. So for any beta, we look at the projection of our map J into the beta structure, and then from this we get this extender and we get the corresponding elementary embedding. Now, if we take any two betas, yes, beta and beta prime, then we get the corresponding extenders for each one of them. Now, it turns out that if for a fixed A, for a fixed finite subset of kappa, the two extenders are the same. Why? And this is because the subset chain preserving condition. Okay, this is exactly the condition that allows us to work with simultaneously with all these extenders E sub beta given by any beta in our set of structures. Okay, and that's the important thing. Why is this important? Well, because thanks to this fact, now we can put all these extenders and the corresponding maps together in a coherent way. So we can define those maps kappa, beta, beta prime from the corresponding limit models corresponding to each one of the extenders. And this is all now it's all well defined and works fine. All these maps commute with the corresponding extender embeddings. And so we can take the direct limit. And this direct limit embedding is, so can you see the pointer? No, I'm not sure. Well, it doesn't matter. Okay. So we get this limit elementary embedding, and then we can take the transitive collapse, and this is okay. Then when we take the supremum of I prime, namely these are all remember I primes are all is the set of all ordinals that correspond to structures A betas, yes, for beta less than kappa prime. So when we look at this supremum, whatever it is, this supremum has to be in Cn because it's a limit of cardinals in Cn, and it's bigger than kappa because, well, because that's what we did. We picked some structure that lived in some A beta for beta greater than kappa. Okay, then we can show that the image of kappa under this limit embedding is precisely this supremum. And therefore, the critical point of this embedding is at most kappa again. But it has to be exactly kappa because of the faithfulness condition. If you pick any beta that is below kappa, then the corresponding map, the corresponding extender is trivial, and the corresponding map is the identity. So the critical point of this limit embedding has to be exactly kappa. And also, V psi is the union of all V betas for beta in I, because we check this for every beta. We just take the supremum. So V psi is contained in N. But this shows that kappa is psi super strong, and therefore psi was bigger than lambda. So it's also lambda Cn super strong, and that's exactly what we wanted. So I went pretty quick here. So, but I think it's, I just wanted to show you a bit where these notions of faithfulness and subset chain preserving are used and why they are important. Okay. Right. So the theorem is this. This gives an exact characterization of the Cn globally super strong cardinals with pi n strong product structural reflection. So this strong product structural reflection characterizes exactly the super strong or globally super strong cardinals of Cn globally super strong. Okay. Right. Okay, so we have now yet another hierarchy of cardinals that correspond to some natural principle of structural reflection, in particular this strong product structural reflection. So we see this pattern repeating again in the large cardinal hierarchy, yeah, from super compact to Vopenka in the case of simple structural reflection, from strong to Woodin in the case of product structural reflection, and now we go from globally super strong to Cn globally super strong for all n simultaneously in the case of this strong product structural reflection. Of course, these cardinals are not as popular as a strong or super compact or extendable and so on. So I don't know. I think the fact that they are equivalent to this very natural form of product reflection, product structural reflection, it's an indication that they should be useful for something. I mean, probably there are applications waiting for this kind of large cardinals using them in the form of this kind of reflection for products. There may be applications. I would say I'm pretty sure there are applications of this strong product structural reflection in algebraic topology or homotopy theory. Anyway, but this is to be explored. I don't know yet. Right. So okay, so that in the last 10 minutes or so that I have, I want to tell you just a little bit about some very recent work we have done with Philip Lucke. And okay, so the motivation is to try to get some cardinal notions that go beyond Bopenka's principle also into this frame of structural reflection. So all the cardinals we have seen so far live below or are don't go beyond Bopenka's principle in terms of consistency strength. So in our work with Philip, we have considered another kind of structural reflection, which is exact structural reflection. What is this? Well, if we have two cardinals, lambda bigger than kappa, then the exact structural reflection for a given class C of structures at kappa and lambda, it just says that for every structure in the class of rank lambda, there is one structure in the class of rank kappa and an elementary embedding from B into A. Okay, so this is exact because we are looking at reflection from structures of rank lambda to structures of rank kappa. Okay, this seems to be a rather natural notion. And if this happens for a proper class of lambdas, then we say that this is the unbounded exact structural reflection. And again, I mean, the proper formulation of this for definability for all classes of a given degree of complexity of their definition, we use this form. Okay, so gamma p ESR kappa lambda means exact structural reflection at kappa and lambda for all classes of structures that are gamma definable. Gamma can be sigma n or pi n using parameters from P. Now, in this kind of exact structural reflection, one has to make an important distinction between classes that are closed under isomorphic copies from those classes that are not. Well, if a class is sigma n definable for n at least one, the closure of this class under isomorphic copies is still sigma n. Okay, so, but when we look at the corresponding principles, if we restrict only to classes that are closed under isomorphic copies, and this is why we put this IC here as a superscript, then actually this is a weaker principle. Okay, so let me tell you some things we know. Well, first thing to notice is that in the case we have closure under isomorphic copies, then the principle of exact structural reflection is even more natural because it says that it holds even only for every structure in the class of cardinality lambda, there exists an elementary embedding of a structure of cardinality kappa into B. Yes. So so once we have closure, if C is closed under isomorphic copies and kappa and lambda are inaccessible, then this principle is even more natural or even simpler. Now, if we look at exact structural reflection for classes closed under isomorphic copies and are sigma 1 definable, then this is just holds in ZFC because it holds for all uncountable cardinals kappa less than lambda, with the only requirement that the cofinality of kappa is less than or equal to the cofinality of lambda. Yes. So, and you can have parameters in V kappa. right? So this is just provable. This principle, even in the unbounded form, is just provable in ZFC. So not very interesting. On the other hand, if we don't require closure under isomorphic copies, then this principle is quite strong. Even for sigma zero definable classes of structures, it already gives you sharps for every real. So you see there's an important distinction here between the principle of exact reflection for classes of structures closed under isomorphic copies, which case is just provable in ZFC for sigma 1 definable ones, or we don't require closure under isomorphic copies, and then this is quite strong even just for sigma 0 definable classes. We get sharps. And the upper bound, though, is not very high. Actually, it's below a Ramsey cardinal. Okay, so a Ramsey cardinal, if delta is Ramsey, then there are many inaccessibles below that that witness this exact structural reflection for sigma 1 definable classes. Okay, not necessarily closed under isomorphism. That's the main difference. Now, the question is, though, what are the large cardinals that correspond to this principle of exact structural reflection? Well, this is what we call exact cardinals. We are not very creative here with names, but so let's see, what are these cardinals? So we have cardinals kappa less than lambda, n less than omega. We say that kappa is n exact for lambda if for every subset of V lambda there is a cardinal kappa prime in Cn greater than kappa and a cardinal lambda prime in Cn plus 1 greater than lambda, there is an elementary substructure of V kappa prime that contains V kappa and kappa, and there is an elementary embedding from this X into V lambda prime that sends kappa to lambda, and A is in the range of J. If we require, in addition, that the image of the critical point is kappa, then we say that kappa is parametrically inexact. Okay. So if you look at the case n equals 0, then these requirements that kappa prime are in Cn it's not needed anymore, and we just require that lambda prime is in C1. So in fact, you can look at this embedding J as an elementary embedding from some elementary substructure of some cardinal kappa prime greater than kappa into, for example, H lambda prime. Yes, it will be the same thing. Okay, but this is the general formulation for every n. We want, as always, we want to look at classes of definable classes of structures as the complexity of definition increases, then this is why these Cn requirements are needed. Okay. All right. Now, and we say that kappa is n-exact if it is n-exact for a proper class of cardinals lambda. All right. So here's the theorem. So the least n-exact cardinal is also parametrically n-exact, and it's exactly the least cardinal for which this exact structural reflection holds for all sigma n plus 1 definable classes. Okay. So these are the cardinals that are characterized by this principle of exact structural reflection. So these are cardinals that have not been considered before, as far as we know. And well, the fact that they are equivalent, that the existence of such a cardinal is equivalent to the existence of a cardinal kappa satisfying this exact structural reflection, this makes one wonder whether, you know, this cardinal should have some possibly more important role at proving things, whatever, or in some applications. So again, I think this is interesting also because something that on the one hand is very natural, this exact structural reflection is very natural, especially if kappa and lambda are inaccessible and we allow for closure under isomorphic copies. This is a very natural principle of reflection. And it turns out that this is equivalent to this notion of large cardinal that was not considered so far. So now the question is, where do these cardinals, these n-exact cardinals, fit in the large cardinal hierarchy? Well, let's see. Okay, so they fit between huge and almost huge. So everyone knows what huge cardinal is. So kappa is huge if there is an elementary embedding from B to M transitive with critical point kappa, and M is closed under J of kappa sequences. And it's almost huge. Kappa is almost huge if there is an elementary embedding with critical point kappa, and M is closed under gamma sequences. And you have such an embedding for every gamma less than J of kappa. That's almost huge. So if kappa is huge, witnessed by some J, then it is parametrically an exact for J of kappa. So the principle of exact structural reflection holds at kappa with respect to J of kappa. Yes. And this holds for all classes of structure, for all definable classes of structures. No restrictions on definability, all of them. So this gives an upper bound on the existence of kappa and lambda that satisfy the exact reflection principle for all definable classes of structures. So if kappa is super huge, then it's n parametrically exact, because then you can go, J of kappa can go as high as you want, so you have it for all, yes? So you have the unbounded form. So super huge is the upper bound for these unbounded exact structural reflection principles. And the lower bound, or a lower bound, is given by this. So if kappa is parametrically zero exact, just for zero exact, then kappa is almost huge with target lambda. And not only that, but there are many almost huge cardinals below, in the sense that the set of almost huge cardinals with target kappa is stationary in kappa, and the set of almost huge cardinals with target lambda is stationary in lambda. So these cardinals fit in the large cardinal hierarchy strictly between almost huge and huge. They are in this region, and certainly well above almost huge. So they do go beyond Popenka's principle, because Popenka's principle has consistency strength slightly below almost huge. Okay, so I think these results are interesting because they are the first we know of that show that some very natural form of structural reflection gives you cardinals that go beyond Popenka's principle. We have more results with Philip. We have generalization of this exact structural reflection, in which you have reflection not just from one lambda, but from a sequence of lambda simultaneously. So they are kind of general or very strong forms of Chang's conjecture. And then we get even more strength. So we have also some results involving I0 I1 embeddings and I2 embeddings and so on. So we are working on this region now, exploring what kind of structural reflection principles can give us cardinals in this region. Okay, so time is up. That's all. Thank you very much for your attention. And thank you very much, Sakai, for all your work and all your friendship during for more than 30 years now. I think we know each other. So congratulations, and I wish you all the best for the years ahead. Thank you. Oh. Yes, York is not there, so I'll take questions if you have any.
Okay. Questions, comments?
So I guess I have a question with this very final stuff. You've got between almost huge and huge. Are you kind of confident you can push it above up to huge and beyond, or what's your feeling?
Well, as I said, you can strengthen this exact structural reflection by requiring not just that you have one lambda, but you have a sequence of lambdas. Yes, and
Right.
then you reflect structures at those ranks to structures at some lower ranks here. Yes, so not just for one particular structure of certain rank, but for a sequence of structures simultaneously, and this seems to be much stronger.
I mean, would that correspond to n huge or something like that?
Yeah, I think I'm not sure this is exact, but I cannot say that now. I mean, but it certainly goes higher.
Okay.
And we have some implications like getting those principles from an I1 embedding, and they imply many I2 embeddings or something like this.
Okay.
So yeah, there is a lot to be said at this region above Bopenka, huge and super huge, and I don't know how far this can be pushed, but certainly in this region there are these natural reflection principles at play. That's for sure.
Okay, great, thanks.
Okay, other comments, questions? Sakai.
I cannot hear you. You have your microphone muted. Can you unmute your microphone? Sakai. Yeah, your microphone is muted.
Yes.
Can you unmute him or?
Let's see. Sakai, can you hear me?
Oh, yes. Yeah, sorry. Now it's on. So do you hear me, right?
Yes, now we can.
Yeah,
Yeah.
okay. Thank you very much for the talk. And I wonder very much when this picture was taken. But in any case,
this was in the 2018 meeting in Montseny in Catalonia. Sakai, he's gone now. Oh.
Wait, what's happening here?
He's muted again. Sakai, you're muted again.
so sorry, the connection is not very good. So do you define something different when you use? So there was reflection in terms of products, right? So if you consider not the full product, but some restricted product, do you get perhaps something different, or it doesn't matter if you do that?
Yeah, possibly. I mean, I haven't looked at this, but you're right. I mean, there are other possibilities here of exploring this product form. Yeah, I'm sure there are other options or restrictions that you could look at. Yeah.
So there are so many different large cardinals notions.
Yeah. Yes, we have possibly too many of them, and we need perhaps more applications of them to make them more interesting.
in reverse mathematics, I think when they obtained too many different systems, they talked about a zoo of systems, and perhaps this is something like that here.
Yeah, we have a big zoo now. Yeah, yes, that's true. But I hope, actually, this is one of the motivations of studying this structural reflection, because somehow it puts order into this mess.
Right.
So you see, when you look at the large cardinals under this perspective under this idea of structural reflection, then you get these characterizations of already known large cardinals in those terms, and you see a similar pattern repeating over and over at different levels of the hierarchy. So this somehow helps to understand it better, and as I said, to put some order on it. I hope this is helpful, at least in this way, and hopefully in applications. Our experience in the work we did with Adrian Matthias, Casacuberta, and Rositsky a few years back on applications of the structural reflection principle to algebraic topology, homology, homotopy theory, and so on. So this was very helpful. I mean, the fact that you have those cardinals like supercompact and extendable and Vopenka expressed or reformulated in this way made the applications much more direct. So the same happens with the analysis of the weak Vopenka principle we did with Trevor Wilson. The fact that we can bring weak Vopenka principle, and so the region between strong and Woodin under this, or this Woodin is equivalent to weak Vopenka principle. That's what Trevor Wilson showed. And so the fact that we can bring all those cardinals into this framework of product structural reflection should make them easier to apply to questions in category theory or algebraic topology or whatever. But there's a lot of work to be done there, and I hope someone does it. I don't know enough category theory or algebraic topology to do that myself, but hopefully some people who can bridge the gap between set theory and those areas could do it.
Yeah, thank you.
I'm looking at Andrew now.
I can feel you looking at me.
Okay, other questions, comments? David?
Just to create some more mess, is there anything that corresponds to anything natural corresponding to strong compactness? Is there anything?
Well, not that I know of. Yeah, that's a big gap in our analysis or in our use of structural reflection to characterize cardinals. I don't have any characterization of strong compacts or delta strong compacts in terms of structural reflection. That would be very interesting if we can get a natural structural reflection principle that is equivalent to those cardinals. Yeah, very good question. Yeah.
Okay, other questions? Okay, if not, let us thank Joan for his very nice talk. And
thank you.